Hello everyone. Nowadays so many traffic rules are there and we all aware of that. Among them, speed limit is so important and maintained by probably all of us. Do you know why? The reason is automated e-challan issued by the authority for cross the speed limit. But do you ever think how they do so without any error? Yes, it is a very useful and interesting properties of mathematics. It is nothing but the Rolle's theorem. So, at first, let us try to understand the statement of this theorem. So, in the statement it says that a real valued function fx defined on a finite closed interval ab such that fx is continuous for all x in ab, that is the closed interval ab. If dash x, that is the derivative of the function, exists for all x in open interval ab and f of a is equals to f of b, then there exists at least one value c lies in between a and b such that f dash c is equals to 0. So, few things are very important here and you should be noted. First of all, it is the real valued function and the function should be continuous within a given interval. The interval should be a closed one. Next, the derivative of the function should be exist in the open interval. That means at the boundary, that means at x is equals to a and at x is equals to b, not necessarily the derivative exists for the function. One more property is what? That at the end point, that is at the a and at the b, the functional value should be equal. If these three properties will be hold for a real valued function, then we definitely find out at least one value c. More than one value also be possible, but at least one value we will find out in between the interval a and b such that the derivative at that point c should be equals to 0. So this is our Rolle's theorem. So now we just explain the theorem geometrically so that we can understand it better. So the geometrical interpretation of Rolle's theorem for, we can say that let this one is the function fx. This one is the function fx. And as for the given situation, the function is continuous. Continuous means there is no break in the function. And not only that, in each and every point of this function, the derivative exists. What does the meaning of the derivative? Derivative means it is nothing but the tangent at each different points. Whatever be the point you can consider on this function, at each and every point we can draw a tangent. That tangent is nothing but the derivative at that particular point. And one more condition is what? That suppose a is the starting point and b is the end point. That means this is the given range basically. Not this one. Actually here this one is the given range and at the point x is equals to a, the functional value fa is this one. And similarly, at the point x is equals to b, the functional value fb is this one. So, this one, these two values should be same. fa should be equals to fb. So, if this one is the given situation, then during this journey or during the entire function, we will find out definitely at least one point. At that point, if you draw the tangent, then that tangent should be parallel to the x-axis. Better to say, if we join these 2 points a and b. So, when we join these 2 points, so this one definitely it is the parallel to the x-axis. And during the function, we will find out at least one point where the tangent is parallel to this line joining AB and hence it is parallel to the x-axis. So let us define this one through some more examples. So here is few more curves. Suppose this one is the given function. Here look, 2 points are there at which if we draw the tangent, then these are parallel to the x-axis. So we will find out 2 points here where we will find out the derivative of the function is 0. So derivative 0, that is actually the tangent is parallel to the x-axis. Is it not? Because both are parallel. So this one, its tangent means its angle, tan angle with the x-axis is 0. And the same for this tangent also. Similarly, instead of this one, if we define this function, here we will find out one point which is parallel to the x-axis. Not only that, if we just take this one, so just this one is a half circle. Here within this one, a point C will be found, and this is nothing but the point which passes to the center of the half circle. And one thing is very important here, that is at the end point. At the end point of this function specially, we will find out that the derivative doesn't exist. Yes, derivative doesn't exist. So you know when derivative doesn't exist? If we will find out that at any particular point the tangent is perpendicular to the x-axis, then at those points we will not found any tangent. Not only that, if we will have any corner point, like if a curve is like this one, so this type of corner point if we will have in a graph, then at those points tangent, such type of points for derivative doesn't exist. Not only like those corners, but if any cusp point you will find out, or any cusp value we will find out in a given curve, then at those points also derivative doesn't exist. I hope you know all about these derivatives while we go for the function. Anyways, let us do some example for the Rolle's theorem. So first example is fx is equals to x square minus 5x plus 6. This one is a given function within the interval 2 and 3. This is the closed interval. Now we are supposed to verify that Rolle's theorem is applicable for this function or not. So first of all, the given function is a polynomial function, and a polynomial function is always continuous. Not only that, it is differentiable also. So the given function is continuous within this closed interval, and its derivative is 2x minus 5. So that one. So its derivative, which is again a polynomial, hence it is derivable also within this open interval. Now at the end point is at the point 2 and the 3. The functional value becomes 0 for both the cases. So we can say that f of 2 is equals to f of 3. So all the three conditions of Rolle's theorem are verified here. So that we can say definitely there exists a point C lies in between 2 and 3 in such a way so that the derivative at that point should be 0. So we know the derivative of the given function is 2x minus 5. If we substitute x for c, we will substitute that, we will get that 2c minus 5, which should be equals to 0, and that will give us c is equals to 5 by 2, that is 2.5, which is lies between 2 and 3. So that we can say the Rolle's theorem verified for this function. Not only the polynomial function, but the trigonometric functions, if you will find out, then these functions are also always continuous and differentiable. Anyways, let us do the second example. Here the given function is. So this one, I hope you can understand which equation is this one. If you don't know, then I can just give you a guess that it is a circle probably. Not probably, this is the equation of the circle. Anyways, so here given that the x lies in between minus a to a, where a is called the radius. So for this function, we are supposed to verify that the Rolle's theorem verified or not. So the given semicircle here, the given interval is minus 1 to 1 and the radius is greater than 0. So that this given one we can draw in this way. I am just drawing the semicircle. So this one definitely continuous within the minus 1 to plus 1 and differentiable also within the open interval only, not at the point this one and this one, because at these extreme 2 points we will get the vertical tangent. As the vertical tangents we will find out, so vertical tangent doesn't exist actually at these 2 points. That means derivative doesn't exist. Now at the end point, the functional value becomes 0 for both the cases. Thus, all the 3 conditions of the Rolle's theorem verified, and hence we can say there exists point C for which we will find out if dash C is equals to 0. And the derivative of the given function is minus of 2x divided by 2 root over of a square minus x square. If we substitute C instead of x, then we will find out this value, which when equating to 0 gives us the value C is equals to 0. So 0 definitely lies in between minus a to plus a. Hence we can say the Rolle's theorem is verified for this given function also. Now let us take one more example, and the example is now fx is equals to mod x and within the range minus 1 to plus 1. So at first let us draw the graph of the given function. So according to the given function, the graph should be this one. Here this is the minus 1 and this one is the plus 1. So given function fx is equals to, we should write minus x within the range minus 1 to 0 and is equals to x within the range 0 to 1. So obviously the given function is continuous within this entire range, but at the point exactly 0, at the point this 0, the derivative doesn't exist, because if we take the left hand side and the right hand side derivative, then we will find out once the value is minus 1 and another side the value is plus 1. So the derivative doesn't exist at this point, so that Rolle's theorem is not applicable, because in between the interval there is a point where the given function is not differentiable. That's why Rolle's theorem is not applicable for this particular function. So these are the few examples for you. Now there are few do by yourself questions. So do these questions by yourself. So the first question is fx is equals to 1 by 2 minus x square within the interval minus 1 to 1. Second one is 1 minus x to the power 2 by 3 in the same interval. Then one more, it is fx is equals to 2x cube plus x square minus 4x minus 2 within the interval minus root 2 to plus root 2. One more is tan x within the interval 0 to pi, and one more, it is 1 by x plus 1 by 1 minus x within the interval 0 and 1. This particular problem for this is actually the exceptional significance, because this one is the very good example by which we can show that the 3 conditions of Rolle's theorem are sufficient only, and by no means they are necessary. Actually, what happens at the point 0 and 1, this function doesn't exist. When the value is 0, then f0 doesn't exist because this is undefined. When it is 1, then f1 doesn't exist because that time this one is undefined. So, depending upon that, still if we go by the formulas of the main value theorem, that is Rolle's theorem, then we will find out there exists a C. At that point, if we draw the tangent, then that tangent is parallel to the x-axis. So you just try to solve this one and prove that the Rolle's theorem, its conditions are sufficient only, not necessary by any means. Anyways, I hope you enjoy the Rolle's theorem and you understand. Just try to solve all those questions so that you can understand it properly. Not only in case of the speed calculation, but there are so many applications of Rolle's theorem still exist. So try to find out all of those so that you can enjoy the Rolle's theorem and feel the theorem. Now we are going to discuss about the Lagrange mean value theorem. This is nothing but the extension of the Rolle's theorem. In Rolle's theorem, we know there are total 3 conditions. Here in the Lagrange mean value theorem, we have instead of the 3 conditions, the last condition is absent. That means only first 2 conditions are valid here. So what is the statement at first? Let us see. So if the function is defined on a closed interval AB in such a manner that fx is continuous for all x in AB, closed interval AB, and the derivative of the function exists for all x in the open interval AB, then there exists at least one value C lies in between A and B such that f of p minus f of A divided by B minus A is equals to f dash C. Just compare with the Rolle's theorem, you will find out that f of A is equals to f of B. That condition is absent here. That means if geometrically we want to analyze the theorem, then we will find out that in case of the Rolle's theorem, this 2 points should be same. That means these endpoints are equal. But in case of the Lagrange mean value theorem, we will find out that this is our FA and this is our FB. These two values are different. So if these two values are different, then these 2 points, if we join by a straight line, then we will find out a second line. So now what happened? The given function is continuous and definitely it is differentiable everywhere within the given interval. Now if this one is the situation, then we will find out a C. C means we will find out in between these two values A and B. Definitely there exists at least one C. Remember, this is at least, that means more than 1 point always can be possible to exist. So there exists at least one point where if we draw the tangent, that means at this point if we take the derivative, then this derivative value is definitely parallel to this line, this second line joining by A and B. These two points if we join by a straight line, then at that particular point we will find out a tangent which is parallel to this one. So just look, this value means what, you know, this one is actually here, the entire this value is f of B and this one is f of A. That means we can say this portion is f of A and this entire portion is f of B. So that this portion, only that much is f of A minus f of B minus f of A, is it not? And this length is nothing but B minus A. This entire length is nothing but B minus A. So that what should be the value of this one? This one we can say that f of P minus f of A, this is the, we can say this is the perpendicular and this is the base. So perpendicular by base means it is nothing but the tan theta, and tan theta is nothing but the derivative of the function, is it now? That's so why the formula is here for the mean value theorem is fp minus fa divided by b minus a is equals to f dash c. That is verified. So this is our Lagrange mean value theorem, and this one is geometrical interpretation. I hope you can understand how the Lagrange mean value theorem applied over the real time example. Let us apply the Lagrange mean value theorem. This is MVT, mean value theorem, for the function this one. So what is the function? Fx is equals to x minus 1 into x minus 2 within the interval 0 and half. So the given function is definitely a polynomial function. So as it is a polynomial function, it is continuous and differentiable everywhere for the real x value. So the given function fx is x square minus 3x plus 2, and it is continuous within the interval 0 and half, and definitely differentiable on the open interval 0 and half. Again, the derivative of the given function we will find out as it is 2x minus 3, so this one. And at the end point, that means f0 the value is 2 and f of half the value is 3 by 4. We should require the value because our formula for the Lagrange mean value theorem is f dash c is equals to fb minus fa divided by b minus a. So now this is our mean value theorem, and if we apply, that means if we substitute all those values, then we will find out that the c value is 1/4. All the conditions of mean value theorem is verified for this given function, and hence we conclude that definitely there exists a c. This c value is here, it is 1/4. For at this point we will find out a tangent which is parallel to the value line joining the point a and b. That means which are the end points of the function. These 2 points if we join by a straight line, then we will find out a tangent which is parallel to that particular line. So the Lagrange mean value theorem is verified for this given function. Let us do one more example. So the function is fx is equals to log x, and now the limit is 1 by 2 to 2. So the log function is again continuous and differentiable for all x within the range 0 to infinity. Okay now? So it is a positive function actually. So that fx is continuous within the given range, given closed interval, and differentiable within the open interval, and its derivative is, we know, that is 1 upon x. So its derivative value is known. Now if we substitute the Lagrange mean value theorem, that means if we take the Lagrange mean value theorem and substitute all those values, then we will find out that the c value is 3 by 2 log of 1 upon log 4. So this value is definitely lies in between 1 by 2 and 2. If you want to verify, then for your reference I can say that log 4 base e, its value is 1.3863. You can verify it from the log table also. So if we substitute all those and calculate, we will find out the value of c lies in between these two. Hence the Lagrange mean value theorem verified, and we will find out a particular c within the given interval. One more example let us consider. If a and b are distinct real numbers, then so that there exists a real number c between a and b such that a square plus ab plus b square is equals to 3c square. So here what to do? Let us define the function x cube first, and which should be defined within the range a and b, closed interval ab. After that, if we take the derivative of this function, then it is 3x square. This one is a polynomial function, so it is exist within the range a and b. Now we can apply the mean value theorem here. So if we apply the mean value theorem, then this is the formula, and if we substitute all and simplify, then we will get a square plus ab plus b square is equals to 3c square, which is our required proof. Hence the proof. Now one more question let us do. So it is f test x is 0 is given in the interval ab. Then so that fx is a constant function in ab. So derivative is 0 within this interval, and our requirement is to show that fx is a constant function. So what to do? So at first let x1 and x2 be two arbitrary points such that these 2 points lies in between the interval a and b. Then we apply the mean value theorem, and within the range x1 and x2, what we will do? We just apply the mean value theorem within the range x1 and x2. So within this range, this is the formula for the mean value theorem. So definitely c lies in between x1 and x2. According to the given condition, within this range, this derivative value is 0. So that what we will find out from here, that we'll find out that this one 0 means this one multiplied by 0 means 0, and we will get f of 2 is equals to f of, that means f of x2 is equals to f of x1. So x1 and x2 are two arbitrary points, and they are different, lies within the interval ab. So it follows that the fx is constant in ab. Is it not? Otherwise, how at two different points the functional values are same? Unless it is a constant, it is not possible. Hence the proof. One more very important example is here, and the problem is if test x exists and if test x less than 0 everywhere in a open interval ab, then so that fx is a decreasing function in ab. So now what to do? Again we consider the two arbitrary points within the interval ab in such a manner that x1, x2 entirely lies in between ab. Now applying Lagrange mean value theorem within the interval x1 and x2. So this is the formula for the mean value theorem, and according to the given condition here, if test x is less than 0 everywhere, that's why we can say that one is less than 0. Now as this one less than 0, so we can say from here that x2 minus x1 is always greater than 0. Is it or not? Because just look at the limit here, x1 less than x2 is given, that's why x2 minus x1 always greater than 0. So that part is greater than 0. So if this inequality holds, that means what? That portion should be less than 0. That means x2, f of x2 less than f of x1 whenever x2 is greater than x1. Hence, from here we can conclude that the given function is a decreasing function in AB. I hope you understand all those questions. Now, we are going to give one more different form of the Lagrange mean value theorem. What is that form? That is actually nothing very special, but just changing the interval. Previously, we have started from the interval a comma b. Now, we have changed the interval as a comma a plus h. So, just the interval is changed and the rest is same. Then what happened? F is continuous within this closed interval. F is differentiable on the open interval a comma a plus. Then, f of a plus h, instead of b, we should substitute a plus h, is equals to f of a plus h into f dash a plus theta h, where theta lies in between 0 and 1. Just remember that our form is f of b minus f of a divided by b minus a, is it not? So that one is equals to f dash c. That one is equals to f dash c. Now, what happens here? F of b, instead of b we substitute a plus h, so that we will write down here also a plus h, so it is only h. So that h, if we multiply, we will find out this term. Instead of c, we substitute a plus theta h. Now we can write f of a plus h is equals to f of a plus h into f dash a plus theta h. So now, instead of the interval, if again we change the interval as 0 comma x, then this above form we will find out as fx. Instead of a plus h, we should substitute x, and instead of a, we should substitute 0. So that this one becomes f of x is equals to f0 plus x into f dashed theta x. This particular form is known as the Maclaurin's formula. Okay, so just this different form of Lagrange mean value theorem, we do one more example here. So what is this? The mean value theorem. Just use mean value theorem to prove this inequality. What is the inequality? 0 less than 1 by x log of e to the power x minus 1 by x less than 1. So what to do? Here at first let fx is equals to e to the power x. Then from the mean value theorem, this form if we apply, then we can write directly fx is equals to f0 plus x into f dash theta x, where theta lies in between 0 and 1. Now given fx is equals to e to the power x, so that we should substitute here e to the power x. At the point 0 it is e to the power 0. So x into, at the point its derivative is again same e to the power x, and at the point theta x it is e to the power theta x. So now if you simplify, then we will find out theta is equals to 1 by x log of e to the power x minus 1 by x. We know theta always lies in between 0 and 1. Hence from here we can say this entire value lies in between 0 and 1, and which is our required proof, and hence the result. So if you understand it properly, then one question is here for you. That is your do by yourself question. Hope you able to do this one. So the question is, prove the inequality x divided by 1 plus x less than log of 1 plus x less than x if x greater than 0. Do this question and answer for this question in the comment box. And if you have any doubt regarding the topic, then you should write in the comment box also. Now it is the time for Cauchy mean value theorem. That is one more extension from the Lagrange mean value theorem you see. At first let us discuss the statement. After that I shall give you a real-time example so that we can understand the theorem much better. So statement for the theorem is, let f and g, here two functions are there, be two functions defined on the closed interval ab such that both the functions are continuous on the closed interval ab and both the functions are differentiable on the open interval ab. One more condition is added here, that the derivative of g dash x not equals to 0 for any x within the given interval. If all those conditions will fulfilling, then there definitely exists at least one value c lies in between ab such that f of p minus f of a divided by gb minus ga is equals to f dash c by g dash c. So probably its geometrical interpretation is not found in any book. But what happens here? Just observe the formula very carefully. This one is the distance. Both are the distance value. So this is the distance in between the interval ab for the first function and this is the distance for the second function. And here it is the ratio. This one is what? The derivative of the function, first function, and this is the derivative of the second function and this is the ratio. If we apply the physics here, then we will say that this is nothing but the speed value, speed formula, is it not? Speed should be represented by the derivative of the given function. So the distance ratio is equals to the speed ratio. That means distance covered by the two functions within the given interval should be equal or equivalent. That means their ratio should be equal by the ratio of their speed, that we can see. For example, we can say that suppose two bikes are there and they have started their journey in the same time, and after half an hour, suppose after half an hour they just cover the double, that means one bike covered the double distance of another. That means suppose the first bike if covered the 10 kilometer, then the second bike covers the distance 20 kilometer within the same stipulated time. Then can we have any idea regarding their speeds? Probably, perhaps we can say the speed of one bike is exactly double of the second bike. But in the practical situation that will not happen. Why? Because it is not possible in a live road there one bike started his journey with a uniform speed. It sometimes goes down, sometimes goes up. So but by this Cauchy's mean value theorem if we apply, then from there we can say that in between the entire journey the one bike definitely acquires the double speed of by compared to the another one. Otherwise it is not possible to cover the exactly double distance within the same stipulated time. So that is one thing you can just imagine about the Cauchy's mean value theorem. I just try to give you a geometrical format. So geometrically we can represent this Cauchy mean value theorem this way. Here the two functions are defined, fx and gx, and accordingly the tangent we will find out at a particular c value where they have the same ratio as their distance ratio is. So this is our Cauchy mean value theorem. Now let us do some application, that means few problems on the Cauchy mean value theorem so that we can understand the application of this theorem much better. So first example, verify Cauchy's mean value theorem for the following pair. So what is the given functions? Fx is equals to cos x and the sin x within the range minus pi by 2 to 0. First of all, these two are very known functions to us. So let us take the curve of this one. So this is our sine curve and this is our cos curve. So within the range 0 to pi by 2. So actual feasible curves are this one and this one. Is it now? So now what we will say, that both the functions as they are the trigonometric functions, so they are continuous and the differentiable for all r values, whatever be the real value. In all the real values the functions are continuous as well as differentiable. Now the derivative of the first function, is minus of sin x and the second function is cos x. And definitely g dash x not equals to 0 within this range. 0 is not included, okay, minus pi by 2 is also not included. So now all the conditions for the Cauchy mean value theorem satisfied over here. So definitely we will find out our C lies in between these two, so that we will fulfilling this formula. So if we now substitute all those values, then we will find out that the C value is minus pi by 4. So this value lies definitely in between these two. Hence the Cauchy mean value theorem verified, and the C value is this one. One more problem is given as the function fx is differentiable on the interval a comma b, where a into b is greater than 0 always. Then so that the following inequality holds for the function. So this one, this equality, not inequality, this one 1 by a minus b, then it is the determinant of a b and fb is equals to fc minus c into f dash c. So now how to prove this one? So first of all, it is given that a into b is greater than 0. What does it mean? That a must not be 0 and b must not be 0. Therefore, within this range AB, this does not contain the point x is equals to 0. Now let us consider two functions. One is fx, which is, let us say, fx, small fx, this is by x, and gx is another function, let it be 1 by x. So that we can find out the derivative of this function. It should be, here it is the u by v format, so it is x into f dash x minus fx by x square, and its derivative is simple, it is minus of 1 upon x square. Now if we apply the Cauchy mean value theorem here, then we can say the above two functions within this range, we will find out a value c lies in between a and b, this c value. Then in the Lagrange Cauchy mean value theorem, we will find out fp minus fa, this is capital, and gb minus ga is equals to f dash c by f dash c by g dash c. So if you substitute all those values and simplify, then we will find out it is as a fp minus b fa by a minus b is equals to fc minus c into f dash c. So that part will be matching with the given condition, and this one for we can write 1 divided by a minus b outside. So this portion is nothing but the determinant of this one. Just look at this one. If we multiply these two minus these two, then we will get this one. So we can write this one in the form of this one, and which is our required inequality which we are supposed to prove, and hence the proof. Here is one more example, that is so that at x not equals to 0, the following inequality holds. The inequality is what? That is 1 minus x square by 2 less than cos x. So what to do? Again here we construct the two functions. Let one function fx is 1 minus cos x and another one is gx is equals to x square by 2. How we will take this? We just take here 1 minus cos x, and this is this side, so x square by 2. So we take this is fx, this is gx. Now very simple, if we apply the simple Cauchy mean value theorem and substitute according to this all values and simplify, then what we will find out from here? Just observe here, this is the formula, and if you substitute and simplify, then we will find out that portion. Now what happens? This expression particularly always less than 1 for c not equals to 0. If c not equals to 0, we know this expression is always less than 1. Now what happens here? So as this one is less than 1, we can say this entire thing is also less than 1. So we can write so. So that means we will find out from here this portion is less than 1. So 1 minus cos x is less than x square by 2. So that will imply 1 minus x square by 2 less than cos x. Hence the inequality holds. So now it is your time. So it is do by yourself question. The first question is, in Cauchy mean value theorem, if fx is equals to e to the power x and gx is equals to e to the power minus x, then so that theta is independent of both x and h and it is equals to half. This is your first question. And the second question is, verify Cauchy mean value theorem for the following functions, and the function is given fx is equals to root x and gx is equals to 1 by root x within the interval minus 1 comma 2. So verify Cauchy mean value theorem for these two functions and write your comment in the comment box. this video, we are going to generalize the mean value theorem. We learned till date the Rolle's theorem, Lagrange mean value theorem, Cauchy mean value theorem. Now we are doing the generalized mean value theorem, and that is called the Taylor's theorem basically. Taylor's theorem, we have two formats. Once we will discuss the Taylor's theorem with Lagrange form of remainder, and next we discuss the Taylor's theorem with the Cauchy form of remainder. So now initially let us start with the Lagrange form of remainder of the Taylor's theorem. First of all, it is the statement of the theorem. So the let f(x) be a function defined on the closed interval ab such that n-1th order derivative is continuous on closed interval ab, as it is the generalized mean value theorem. So that we take the nth, or that means n-1th order derivative up to it is continuous within the closed interval ab, and nth order derivative exists on the open interval ab. If it is so, that means if these two conditions will satisfy, then there exists at least one value c lies in between a and b such that f of b is equals to f of a plus b minus a f dash a plus 1 by 2 factorial, then it is b minus a its whole square f double derivative of a. In this way it will continue, and these are the last two terms. The previous to the last term is 1 by n minus 1 factorial into b minus a to the power n minus 1 into n minus 1th order derivative at the point a plus 1 by n factorial b minus a to the power n, and it is the nth order derivative at the point c. C lies in between a and b. Just look, if we just omit all those, only this portion if we consider, then this is nothing but the Lagrange mean value theorem. Is it now? Anyways, so here you just note that the interval is right now it is a comma b. If we change the interval, then we will find out this theorem in different forms. So let us start to verify the different forms of the Taylor's theorem. First of all, we just change the interval from a comma b to a comma a plus h. Then what will be the change in the above formula? So simply instead of b we substitute a plus h. So if we do so, then we will find out here instead of b we substitute a plus h. So that it is f of a plus h is equals to f of a, then plus here h, because b is equals to a plus h minus a means a cancel out, so only h will be left. So h into f dash a plus h square by 2 factorial f double dash a. In this way it will going on, and these are the last two terms. Just observe here instead of c we substitute a plus theta h. Okay, that we will find out while we discussing the Lagrange mean value theorem, the another form of Lagrange mean value theorem, and definitely theta lies in between 0 and 1. So the last term of the above is called the remainder after n terms, and it is denoted by Rn. This term is denoted by Rn. So this is your Rn. Okay, where theta is lies in between 0 and 1. This is called the Lagrange form of remainder. Now it is the Cauchy form of remainder. So what is the Cauchy form of remainder? That is, we will just have the same thing, that is the real valued function fx is given such that the n minus 1th order derivative is continuous within the interval a comma a plus h. We continue with this interval only. Its nth order derivative exists in the open interval a comma a plus h. Then there exists one number theta, where theta lies in between 0 and 1 such that we will find out this formula. Here just look, everything will be same, only change is in the last term. Here the last term is h to the power n into 1 minus theta to the power n minus 1 by n minus 1 factorial, and it is f to the power n a plus theta h. So this last term is called the remainder, and this is called the remainder after n term, and it is the Cauchy form of remainder. If you want to prove this Cauchy form of remainder and the Lagrange form of remainder of the Taylor's theorem, then this proof, if you want this, then you just write in the comment section that you require the proof of these two, then I will give another video for this two. Otherwise, the proofs are available in any standard book. Anyways, here few things should be noted. What things are? First of all, the interval becomes a comma x. That means initially we have started from the interval a comma b. Now we change the interval to a comma a plus h. Instead of b, if we write x, then this Taylor's expansion becomes, instead of b we just substitute x, so that it becomes f of x is equals to f of a plus x minus a f dash a. In this way it will continue. Just instead of b substitute x and we will find out here this one. And definitely this is the remainder after nth term, and it is the Lagrange form of remainder. Within the same interval, if we write in the form of Cauchy remainder, then we will find out this expression. Just here is the change, nothing else. Okay, now. Not only that, now if we change the interval as 0 comma x, a should be replaced by 0 and b should be replaced by x, then we will get this expression. Just look, f of x is equals to f0 plus x into f dash 0 plus x square by 2 factorial f double dash 0. In this way it will going on, and the this term is x to the power n minus 1 by n minus 1 factorial, f to the power it is here n minus 1 0 at the point 0, and plus the last term is x to the power n by n factorial f to the power n theta x. This is the Lagrange form of remainder. And if this type of interval will be considered in the Taylor's theorem, then it becomes the Maclaurin's theorem. So Maclaurin's theorem is nothing very special thing, but it is just the change of interval in the Taylor's theorem. Then we will find out the Maclaurin's theorem. So above all those, these finite series are called the mean value theorem. Whatever be the series till that we have going on here, these all are called the mean value theorem of nth order. Okay, so from here we can say that the third order mean value theorem should be f of a plus h is equals to f of a plus h f dash a plus h square by 2 factorial f double dash a, and this is the remainder term, h cube by 3 factorial f triple dash a plus theta h, where theta lies in between 0 and 1. Similarly, fourth order mean value theorem also we can find out, and here the fourth order derivative contains the nth term, that means the remainder term we can see. So this is the expression for the fourth order mean value theorem, is it not? So depending upon the n value, that means how many derivatives we are considering, depending upon that we can take the MVT mean value theorem of that particular order. So till that, whatever the series we will find out for the Taylor's series and the Maclaurin series, both are finite. What happens for the infinite Taylor series and the infinite Maclaurin series? So first of all, if this function be defined in the interval a comma a plus h such that all orders of derivatives of fx exist in a comma a plus h, that means not only up to the n minus 1th order or nth order, but whatever be that means how long you want to proceed, you can move. So any order of derivative will exist within this given interval, and the remainder Rn should tends to 0 as n tends to infinity. Then the given series becomes the, that means this is becomes a powered series, and this powered series is called the Taylor's infinite series, and we will find out its form as this one, f of a plus h f dash a plus h square by 2 factorial f double dash a, and look here the last term is not finite, it is going to infinity, and definitely this value, entire value is equals to f of a plus h. So we can say that this series is convergent and it converges to the value f of a plus h. So this is just the infinite series where we consider that the Rn tends to 0 as n tends to infinity, that's all. Beside that, whatever be the finite series for Taylor's and the Maclaurin's, you know, that is all. Similarly, for the Maclaurin's infinite series, what to do? Our interval should be 0 to x, and the series becomes this one. Here just look, f of x is equals to f0 plus x f dash 0 plus x square 2 factorial into f double dash 0, and it is going on. So this series definitely converges to the value of fx. So this is our infinite Maclaurin series. So I hope you understand the finite and infinite Taylor series and the Maclaurin series. So its application for, I am going to prepare another video. The previous video we considered the Taylor series and the Maclaurin series, its finite and infinite form both. Just let me clear that before that we know the power series. Actually, this Taylor series and Maclaurin series gives us the power series representation for the different functions such as the trigonometric function, exponential function, logarithmic function, binomial function, etc. Whatever be the functions are there, we can explore it in the power series format. So let us do some example of that kind. Initially, let us start with an example of sin x. So sin x is the given function. So if we take its derivative, then what we will find out? So its first derivative is cos x, that we can rewrite as sin pi by 2 plus x. Next derivative is minus of sin x, and that also we can rewrite as sin 2 into pi by 2 plus x. In this way, if we proceed, then its nth derivative we can write as sin n pi by 2 plus x. So at the point of 0, we will find out, that means f of 0 for, we will find out sin 0 is 0. Then f dash of 0 means it is cos 0 is 1. Again, if double dashed 0 means it is again what? 0. So in this way, the value of all those functions we can find out. Now by the Maclaurin's theorem with the Lagrange form of remainder, that means this is the finite case. Here we will have the series as f of x is equals to f0 plus x into f dash 0 plus x square plus 2 factorial f double dash 0, and the last term, that means the nth term, is x to the power n by n factorial into nth order derivative of f at the point theta x. Now if you substitute all those values, then we will find out sin x is equals to, just substitute all those values, and if you simplify, you will find out it is x minus x cube by 3, because this term becomes 0, this term becomes 0. So x minus x cube by 3 factorial, then in this way it will continuing, and these are the last two terms. Now if you want to take the infinite series of sin x, then just simply Rn tends to 0 as n tends to infinity, so that this series becomes sin x is equals to x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, and so on. So this is our infinite expression of the sin x. Exactly like the sin x, we can do the power series for the cos x also. Just observe, this one is the power series, and for cos x, tan x, whatever be the trigonometric functions we have, for all those we can calculate or find out these type of series. Previously, this we have just used as the formula, but now we can find out that how to find out or how to evaluate this sin x or expand this sin x in the power series format. So if you know the Taylor series and the Maclaurin series, then we can easily expand the function in this type of infinite series. Next we will do with log function. So the given function is fx is equals to log 1 plus x. If we take the derivative of this function, then we will find out the first derivative is 1 divided by 1 plus x, second one is minus of 1 by 1 plus x square, and in this way it will progressing. At the point 0, that means when x is equals to 0, then their functional values are defined in this way. Now if we will take the nth order, then this is its nth order derivative, is it now? And at the point theta x, this is its value. So now if we apply the Maclaurin's finite theorem, that means Maclaurin's theorem in finite form, then we will find out fx is equals to f0 plus x f dash 0 plus x square by 2 factorial in this way, and this is the nth term. This remainder term may be due to Lagrange or may be due to Cauchy. It is depending upon the question. Now if you substitute all those values and simplify, then you will find out the finite series for log of 1 plus x is equals to x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 in this way, and these are the last two terms. And when Rn tends to 0 as n tends to infinity, we will find out the infinite series for the log 1 plus x. So this one also we know as the formula, and now here we prove this one. So in this way we can expand the log series. Not only log series, the exponential series, binomial series also we can do. So these two are the questions which I solve here for you. Now I am giving you few questions for your reference. That means there are few questions given. These questions you just try to solve by yourself. If you can able to do all those, then you can get sure that you understand Taylor's theorem and the Maclaurin's theorem properly. So here are for your questions. So do by yourself questions. So first question is the function cos x. So what you will do, you just do for this first four functions, finite and infinite series both. So the first function is cos x, second is e to the power x, third is e to the power x into cos x, fourth one is e to the power of tan inverse x. Now fifth question is use MVT so that sin x is greater than x minus x cube by 6 if x lies in between 0 and pi by 2. One more question is there. The question is expand the polynomial fx is equals to x cube minus 2x square plus 3x plus 5 in a series of positive integral powers of x minus 2. Remember x minus 2 is here. So b you can say x and a you can say 2. Okay, so that you can progress. Anyway, so one more question is there, and the question is apply Maclaurin's theorem on fx is equals to 1 plus x to the power 4 to find 1 plus x to the power 4 is equals to 1 plus 4x plus 6x square plus 4x cube plus x to the power of 4. One more and the final question for this video is so that limit h tends to 0 theta is equals to 1 by n plus 1, where theta is given by the expression f of a plus h is equals to f of a plus h into f dash a plus h square by 2 factorial f double dash a, and just look, the expression is nothing but the Taylor's theorem. So provided if n plus 1th order derivative of f is continuous at the point a, and this n plus 1th order derivative at the point a is not equals to 0. So this last question may give you some trouble, but before that all 7 questions are so simple, and I am very hopeful that you can able to solve all those questions.
So what is indeterminate forms that you should know? And in this lecture we will come to know about this indeterminate forms and one rule which is called the L'Hopital rule with lots of examples. I hope you can enjoy the lecture. So first of all, what you can able to see here, few limits, and I hope these limits are very much well known to you. Yes, these all are the standard limits, and you know that these all we remember or learn as a formula. Yes, it is limit x tends to 0, sin x by x is equals to 1, that we know. Similarly, log 1 plus x by x when the limit is 0 is 1. Likewise, there are so many standard limits are there. But do you know how these values are there? Is it possible that without remembering all those standard limits, we can calculate the values of those limits? Yes, it is possible. But the thing is, when we come to these type of limiting functions, that time we stuck somewhere because these all are in the indeterminate forms. So first of all, how to find out or how to identify that a function is in indeterminate form? So for that, you just find out a function in the denominator and numerator format. And if we take the limiting value individually to its denominator and numerator functions, then we find out that these limiting values are 0. That means the limiting value of the denominator as well as the numerator both are 0. If it is, then we say the function is in indeterminate forms. So indeterminate forms mean we can say the denominator 0 and numerator 0 means it is in the form of 0 by 0. So in that way, we can say if a function is in the form of 0 by 0, then it is called the indeterminate form. So not only 0 by 0 is the indeterminate form, but there are so many more forms are there, such as here if we shall find out any limiting function where the denominator and numerator are just like infinity by infinity, otherwise it is infinity minus infinity, or 0 into infinity, or 0 to the power 0, or it is 1 to the power infinity, or it is infinity to the power 0. All are these indeterminate forms. But before starting these indeterminate forms, with lots of example, we come to know how a function is indeterminate, and we should identify first of all the indeterminate forms and which type of indeterminate forms are those. After identifying those, we are going to solve those problems. So first of all, let us start with one example. So here it is the first example. Here you just observe the given limit is x squared divided by e to the power x minus 1. Here at first we say that fx, let us consider fx is equals to x square, and gx, that one is equals to e to the power x minus 1. Now if we consider limit x tends to 0, then definitely this functional value is 0. And similarly, if we consider limit x tends to 0, then e to the power 0 is 1 and 1 minus 1 is 0. So that this one is 0, this one is 0 at the limiting condition x tends to 0. So we can say the given limit is in the form of 0 by 0. Is it? So when we find out it is in this form, we identified that it is the indeterminate form and it is in the form 0 by 0. Let us consider the another one. So here again one function is given, and here we can say fx, that one is equals to x e to the power x minus of log of 1 plus x, and gx we can say that it is x square, and very obvious when it is x tends to 0 we shall find out it is 0, so that it is 0, and log of 1 plus 0 means it is 1, log 1 is 0, that we know. So the functional value at the point x is equals to 0, it is 0, and here gx obviously it is 0, so this one is also in the form of 0 by 0. Now one more question is here. So here one more example. So for this one, here it is limit x tends to 1, and this one is given. Here we can say fx, we consider fx is equals to 1 plus log x minus of x, and gx is equals to 1 minus 2x plus x square. So just have a look, when we substitute x tends to 1, that means x is equals to 1, that time we find out this one 0 and this one is also 0. So this is also in the form of 0 by 0. Now consider another function, which is this one. Here our fx is equals to x square and gx is equals to e to the power x. When the limiting value we substitute, limiting value is given here x tends to infinity. So when we substitute, we find out if x is infinity and gx is e to the power x means e to the power infinity, so it is also infinity. So we can say this is in the form of infinity by infinity. So this one is in the form infinity by infinity, and if the form is infinity by infinity, then easily we can convert it into the form of 0 by 0. Just if we write this one as if limit x tends to infinity and 1 upon e to the power x divided by 1 upon x square. So that means what we have done here, we have written here 1 by gx divided by 1 by fx. If we can write the given limit as in this format, then we can say now the limit is a 0 by 0 form. So if we know the 0 by 0 form only, then also by the same process we can solve this limit. Otherwise 0 by 0 form itself also can be solved exactly in the similar manner as we solve the 0 by 0 form. How to solve? Gradually I am coming. Just let me show you a few examples, and we should identify initially that these are in which format. After that we are going to solve all those. So now here one more example, and here it is given that fx is nothing but it is log of x minus pi by 2, and gx is equals to tan of x. And I hope you can understand that here when x tends to pi by 2, then we find out it is log 0. Log 0 is always infinity, and gx is tan pi by 2, tan pi by 2, so that is also infinity. So this is in the form of infinity by infinity. Similarly, one more example let us consider. Here in this example we shall find out that fx, which one is equals to 1 square plus 2 square plus 3 square, and in this way it is up to x square. That is nothing but the sum of the square of the natural number. So we know its formula, and its formula is n into n plus 1 into 2n plus 1 by 6. I hope all of you can remember this one. And here I have written n, but as it is the in terms of x, so instead of n we should write it as x, is it? And if we simplify this one, then we should find out the value for this one is 2x cube, then plus of 3x square and plus of x divided by 6. And we will have here gx is equals to x cube. So in this functions, if we substitute this limit, then we shall find out this fx is tending to infinity and gx is also tending to infinity when x tends to infinity. So the given limit is in the form of infinity by infinity. So one more example is here. In this example we shall find out, and we consider that fx is equals to 1 by x, and here the gx is equals to cot of x. Now when x tends to 0, then fx definitely it is infinity, and gx means cot 0, that is infinity. So this is in the form of infinity minus infinity, is it not? So this is in the form of infinity by infinity. If a given function or a given limiting value is in this format, that is infinity by infinity format, then also we can convert it into the 0 by 0 form very easily. So how, if we want to know that answer? So for that I can see that here if we just simplify this one, so here the entire thing, if we simplify like this one, 1 by x minus cot x, we can write as cos x by sin x. So now if we simplify this one, then we shall find it out as sin x minus cos x and x cos x divided by x of sin x. So now if we say that fx is, the new fx is sin x minus x cos x and gx is x sin x, then when x tends to 0, then sin 0 0, and it is 0 into something means 0. So here it is the 0 and x sin x, definitely this one is also 0. So this one is in the form of 0 by 0. So after getting in this format, that means we just rewrite the given function in this format, we will find out it is in the 0 by 0 format, and it is in the 0 by 0 format means the same process we should apply to evaluate this one. But for generality I can say that if any function in the form of infinity minus infinity form, then we can always convert it into the 0 by 0 form, and the transformation is 1 by gx minus of 1 by fx divided by 1 upon gx into fx. So this one is same as this one, you just evaluate and you just calculate, and we shall find out that the same thing I have written here. Now one more question is here, and in this question again this is in the form of infinity by infinity. Just have a look, because here the fx we can say as x divided by x minus 1, and gx is, it is 1 upon log of x. So again we just simplify and transform it into the form of 0 by 0, and we should proceed to solve it out. Now if your function is in the form sin x log x, so here you just have a look, two functions are again given here. So fx we consider is sin x, and gx we should consider as log x, so that here if we substitute x tends to 0, then sin x that means sin 0, that is 0, but log 0 that is infinity. So it is in the form of 0 into infinity. So this is also the indeterminate form. And if you have this type of format, then you can write as the fx divided by 1 by gx. So that just have a look, we will have the same function. And if we write in this format, then it is in the 0 by 0 format. So after getting in the 0 by 0 format, we can solve in the same process. Now one more question is here. In this question, again it is the fx is it is 1 minus of sin x, and gx is equals to the tan x. And if we substitute the limiting value pi by 2, then we shall find out it is 1 minus sin pi by 2. Sin pi by 2 means it is sin 0 0 and pi by 2 is 1. So it is 0, and tan pi by 2 is nothing but infinity. So that this one is also in the form of 0 into infinity. So that again we just rewrite it into the form of 0 by 0, and we should proceed to solve. Now come to this example. In this example, we have fx is equals to x plus sin x and gx is equals to tan x. That means this one we consider as fx and this one we consider as gx. If this type of form is given here, this value is 0 and tan 0 is also 0. So that we have in the form of fx to the power gx, where fx is 0 and gx is 0 for this limiting case. So that is in the form of 0 to the power 0. If we have this type of forms, then to convert it into the 0 by 0 form, we should take log on both sides. And let us consider y is equals to this entire function and take log on both sides. If we do so, then it is log y is equals to tan x, then log of x plus sin x. Now tan x means when x tends to 0, that value is 0, and log 0 means it is infinity. So this one is in the form of now 0 cross infinity. So this is the indeterminate form, and we know if we have the form 0 into infinity, then how to solve it. So at first we solve this function, and after completion of the solving, we take the antilog to find out the value of y, and hence we will get our desired answer. Similarly, one more example if we consider, then it is here, and here we shall find out that fx is equals to e to the power x plus x, and gx is equals to 1 upon x, and this value is infinity when x tends to infinity, and gx is definitely 0. So it is in the form of infinity to the power 0. So if this form is there, then also we will do the same thing. We take the log on both sides, and we shall find out log y. If we say this one is the y, then log y is equals to 1 upon x, then e to the power x plus x. So this is in the form of now it is 0 into infinity again. So if in this form we can have, then from here easily we can convert it into the 0 by 0 form, and we can solve it. How to solve? I am coming soon. One more example, that is the limit x tends to 0. It is 2x plus 1 divided by x plus 1 whole to the power of 1 by x. So here it is the fx is equals to nothing but it is 2x plus 1 divided by x plus 1, and gx is equals to 1 upon x. So here we shall find out when x tends to 0, then this value is 1, and for x tends to 0, this value is infinity. So it is in the form of 1 to the power of infinity. So if this format is given, then again we take the log on both sides, and we shall find out log of y is equals to 1 upon x. Then it is 2x plus 1, here it is log definitely. So 2x plus 1 divided by x plus 1. And now it is in the form of what? Yes, it is infinity into 0. Yes. So now it is again we can convert into the 0 by 0 form. And one last example for this lecture is this one, and that is x to the power 1 minus x, and the limiting value is x tends to 1. Here we say that fx is equals to x and gx is equals to 1 by 1 minus x. So that when x tends to 1, this is 1, and this one is definitely infinity. Yes, and it is in the form of 1 to the power infinity. So whatever this type of forms we shall find out, we will take the log on both sides, and after taking log, I will get here it is log of x. So this is in the form of infinity into 0. Yes, and infinity into 0 means it is in the form of 0 by 0, easily can be converted and we can solve it. Now the question is, all those examples are given, there are so many, 14 examples are given, and we can identify that a specific given function are in which format. These are all in different formats, and whatever those examples we have here, no one can be solved in our usual method because these all are the indeterminate forms. So now let me just give a brief summary that there are indeterminate forms means either the given function is in the 0 by 0 format, otherwise it is infinity by infinity format, or it is infinity minus infinity format, or 0 into infinity, or 0 to the power 0, or 1 to the power 0, or infinity to the power 0. Any of these form are in the indeterminate form, and if these are the formats, then these are the functions we can write here. Infinity by infinity, all are the in denominator form. So two functions definitely included in the indeterminate form. One is fx, another one is gx. If it is infinity by infinity, then fx by gx is there, and definitely both for the limiting case tending to the limit infinity by infinity. Similarly, if this one is a function, so then fx and gx, and both are tending to infinity by infinity. And these are we consider one as fx, one as gx. Here it is fx to the power gx. Here also all are same. So after getting this way, what we will do here, if this is in the infinity by infinity format, then always we can convert the function in this way to get our 0 by 0 format. Similarly, if it is infinity minus infinity, then we should convert the function into the 0 by 0 format by this transformation. For 0 into infinity, this is the transformation, and for all these three, the transformation here it is for fx to the power gx, we take log on both sides, so that we will get this type of form, and which is definitely in the form of 0 into infinity. So once you will get the 0 into infinity, then from there, if we apply this transformation, then we shall find out it is into the 0 by 0 format. So ultimately, whatever the different forms are, all are converging towards the form of 0 by 0. So if we know how to find out the value for the indeterminate form 0 by 0, we can able to solve any other indeterminate forms. So if we want to solve these indeterminate forms, then here is the rule. So what is this rule? This is called the L'Hopital rule or L'Hopital theorem. What the theorem says? Here two functions are given. So let fx and gx are the two functions which are real valued functions in such a manner that the limit x tends to a, fx is equals to 0 or infinity, and gx also tending to the same value 0 or infinity. That means if fx is equals to 0, then gx is also 0, and if fx tends to infinity, then gx should tend to infinity. And the derivative of this function at this point, that is f dash a and similarly g dash a, both should exist where definitely g dash a not equals to 0. If it is so, then we can have that limit a tends to, that means limiting value for this fx by gx should be equal to the limiting value at this limiting point, that means f dash a divided by g dash a. That means it is very simple. Just fx by gx, whatever it is be given, if it is in the 0 by 0 format or it is in the infinity by infinity format, we just simply take the derivative of fx and derivative of gx. After that, we should find out that this derivative of gx at this limiting point is 0 or not. If it is not equals to 0, then whatever be the derivative forms you shall find out, just substitute the limiting value, and whatever be the value you shall find out, that is your result. So let us do this one with the examples solved. That means so many examples we have in this lecture, and all those examples now we are going to solve. So at first it is the first example. Here we know that fx and gx, and then let me write it as limit x tends to 0, then it is x square divided by e to the power x minus 1. So that one is we just take the derivative of the denominator and numerator. So just let me write down limit x tends to 0. Then the derivative of x square means, I hope you know, that is 2x, and the derivative for e to the power x minus 1, if we consider, then it is only e to the power x, because derivative of 1 is 0. Now we just check that when we substitute x is equals to 0, then this value is what? It is e to the power 0 means 1, which is not equals to 0. That means we should stop here and we just simply substitute the value of this x. So if we substitute, then we shall find it out as it is 2 into 0 divided by e to the power 0. That means it is 0 by 1, that is 0. So this is the value. Okay, so I think it is very simple. Let us do the next one. So for this next one, again we just write it down, limit x tends to 0, and then it is x e to the power x minus of log 1 plus x divided by x square. Very simple. We again take the limit on, that is we take the derivative on denominator and numerator. And if we take the derivative, then I hope its derivative is very simple. It is 2x. And if we take the derivative for this one, then it is the x e to the power x, means x is the first function, e to the power x is the second function, then plus derivative of the first means 1 and the derivative of second means this one, and log for, we know the derivative is 1 upon the given function, so it is 1 upon x. Now the derivative of x is 1, so it is all. So after getting this one, if we substitute the x is equals to 0, then x, this part is 0, e to the power 0 means 1, and here it is minus of 1, so it is 0 divided by 0. So this derived form is again in the form of 0 by 0. So we will do the process again, that means we just repeat our process. So after that we again take the derivative of denominator and numerator both, so that now we will find out what it is. If we take the derivative of, for this one, then it is x e to the power x plus e to the power x. The derivative of e to the power x is e to the power x, and the derivative for this one means it is 1 plus x its whole square, and then it is minus of 1. I hope you know the derivative, and after that it is 2. So definitely it is not equals to 0, so we should stop our process here, and after that if we substitute the values, then we shall find out, here it is 0, then this part is 0, then e to the power, here it is 2 into e to the power x. So it is 2 e to the power 0 means 2 into e to the power 0, and here it is, if we substitute 0, then it is 1 divided by 1 plus 0 its whole square, and divided by 2, so that means it is 2 and it is 1, so it is 2, then it is minus 1 divided by 2, so it is 1 upon 2. So this is our answer. Now the third question. So for the third question, what we will do here, so if similar process, we will take the limit x tends to 1 here, so it is the 1 plus log x minus x divided by 1 plus 2x minus of x square, here it is plus and this is minus. Okay, so if we just simply take the derivative for denominator and numerator both, so that it is 1 by x minus of 1, and here we shall find out it is minus 2 plus of 2x. So now if we substitute x is equals to 1, then we shall find out it is 0 by 0. So this is again in the form of 0 by 0. That means we do the process again. That means we repeat our process again. So again if we do so, then we shall find out, here it is minus of 1 upon x square, then divided by it is 0, so that it is only 2. Now if we substitute the value, here just look, this one is not equals to 0. That means we should stop our process here. Now if we substitute the value, then we shall find it out. Here it is minus of 1 upon 2. So this is our answer. So I told you that if the form is infinity by infinity, then we will do the same process. No change is required. That means that is not at all required to convert it into the 0 by 0 format. So that if we do so, then here we shall find out limit x tends to infinity. It is x square divided by e to the power x. We take the derivative for the denominator and numerator both, so that we shall find it out, this one. And now if we substitute, it is again in the form of infinity by infinity, yes. So that we do the process repetition. So it is given us, it is 2 divided by e to the power x. So now we shall find out it is 2 by e to the power of x. That means e to the power infinity by 2 which is not in the form of infinity by infinity anymore. So now we shall find out here that 2 by infinity, so anything divided by infinity is 0. So the limiting value is 0 here. Now the next question, in the next question here it is the limit x tends to pi by 2, and if we take it is the log of x minus pi by 2 divided by 10x. So definitely we take the derivative for the denominator and numerator, so that we shall find it out as 1 upon x minus pi by 2, and its derivative is 1, so let it be. And then 10x, its derivative is 6 square x, so that we can rewrite as limit x tends to pi by 2. Sec square means we know this is 1 by cos, so it is cos square x divided by x minus of pi by 2, which is in the form of, if we substitute, then we know cos square pi by 2 cos pi by 2 means it is 0, and here it is 0, so it is in the form of 0 by 0. So we will take again the derivative, so that it is limit x tends to pi by 2. If we take the derivative, then we shall find out the value as minus of 2 cos x sin x, and then divided by 1 only, which is no more in the 0 by 0 format. And now if we substitute these values, then we shall find out the value is 0. So this is the limiting value. Now one more example here. So if this one we are going to solve, then here it is the limit x tends to infinity. Definitely we substitute this one instead of this fx. So it is 2x cube plus of 3x square plus of 6 plus of x divided by, here it is 6 into x cube. Now if we take the derivative, then it is, we shall find out limit x tends to infinity, and it is 6 of x square plus of 6x plus of 1 divided by 6 into 3 means 18 of x square, which is again in the form of infinity by infinity. So we take the derivative again. So if we take the derivative again, then it is 12x plus of 6 divided by 36 of x, which is again in the form of infinity by infinity. So one more time we should take the same process. So finally now we shall find it out. It is 12 by 36, which is nothing but is equals to 1 by 3. So which is our value for this limit. So now if our form is infinity minus infinity, then we should rewrite the given term in this format that we continue, and after that it is in the form of 0 by 0. That's why what we will do here, we just find it out that limit x tends to 0. Here if we simplify this, then we take the derivative in the denominator and numerator, so that it is cos of x minus first function derivative of second function, but cos x, its derivative means minus will be there, so then it is cos of x, and then divided by first function derivative of second, then minus plus of the sin x. This is the derivative, and this to cancel out. So after that we shall find out this format, which is again 0 by 0 format. So it is in the form of 0 by 0. So we will do the things same, and we just repeat the process once more. So this is limit x tends to 0, and if we take the limit, so that is the derivative, so that we shall find out x cos x, because x sin x is there, first function derivative of second, plus of second function derivative of first. After that here also the first function derivative of second, then plus of derivative of the second function, it is the cos x, so its derivative is 1, then plus of it is the cos x. This one is 0, but here we shall find out 2, because cos 0 is 1, cos 0 1, so 2. So finally we shall find out 0 by 2, that means 0 is the limiting value. Now one more question is here. In this question, if we want to solve, then again this is in the form of infinity minus infinity. We should convert it into the form of either infinity by infinity or 0 by 0. So if we want to do so, then it is limit x tends to 1, and we just simply take the LCM. So if we take the LCM, then we shall find out it is log of x, and it is x log x minus of x, then plus of 1. So now if we just substitute the value x is equals to 1, then we shall find out it is 0, and this is 0, this is 0, so it is in the form of 0 by 0. So after that we take the derivative on the denominator and numerator, and we shall find out x into 1 by x minus of log x, it is plus of log x, then minus of 1, then divided by x minus 1 into 1 upon x, then plus of log of x. So this is 1 and this is minus 1, so this portion will be cancelled out. So log x, log 1, I know, that means we know that it is log 1 is always 0. And here it is, if we just separate x by x, that means 1 minus 1 upon x. So for that it is 0 and log 1 0. So it is again in the form of 0 by 0. So if we simplify, then we shall find it out as, here it is 1 upon x and here for it is 1. So it is minus of 1 upon x square, then plus of 1 by x. So from here we just simplify and we just do one thing. Here we take 1 upon x common, and if we cancel it out, then it is minus of 1 by x plus 1. Now it is not in the form of 0 by 0, and if we substitute x is equals to 1, then is x is equals to, sorry, here it is 1. So then we shall find it out that it is 1 by 1. So it is 0. Sorry, this becomes plus because here already minus is given and 1 upon x is there, and if we take its derivative, then it is plus of 1 upon x square. So it is plus, so we shall find it out, it is equals to 1 upon 2, which is the limiting value. So in this way we can easily calculate the indeterminate forms. So now come to this function, and here we shall find out that it is limit x tends to 0, and we just rewrite in the form of 0 by 0. So that we just write it down as log of x, suppose it is divided by 1 upon sine x, which can be again written as log of x divided by 1 upon sine x, means we know that it is the cosec x. Now log 0 is infinity, so this is in the form of infinity by infinity. So as it is infinity by infinity, the same process we follow, and we just simply take the derivative of the denominator and numerator, and here by taking the derivative we just find out the cosec x, cot x. So if we simplify, then it becomes cosec means 1 by sine, cot means cos by sine. So that we shall find it out from here, it is the sine square x divided by x into cos x. Here minus sign is there, so limit x tends to infinity is also given. Okay, so again now if we substitute the value, then it is the it is 0. The limiting value is given as 0, not infinity. So sine 0 0, cos 0 1, but here it is 0. So this is again in the form of 0 by 0. So as it is in the form of 0 by 0, so that we just simply again take the derivative, we take minus outside, so that limit x tends to 0. Now its derivative is 2 sin x cos x, and its derivative is first function, derivative is cos x, its derivative is sin x, so it is minus then plus of cos x finally. So now from here we just substitute the limiting value, so that we shall find it out that this one is 0 and it is 0 and cos 0 is 1. So it is no more in the 0 by 0 form, so that it is minus of 0 by 1, so that it is finally 0, so that the limiting value is 0. Now let us go for the another question. So the another question is this one. Here again for the given function is limit x tends to pi by 2, and it is in the 0 cross infinity, that means 0 into infinity indeterminate form, and that we should again rewrite in the form of here it is 1 minus of sin x divided by tan x, means we can write it as cot x. So now if we substitute the pi by 2 value, then we shall find out it is 0 by 0 form. So it is the form 0 by 0. So in this form 0 by 0, if we just simplify, then we can find it out as we take the derivative, and it is the minus of cos x, and cot x means it is minus of cosec square x. So now if we just simplify again, that means we just simply substitute the value pi by 2, then if we substitute, so then we find out that this cos pi by 2 is 1, cos pi by 2 is 0, whereas cosec square pi by 2 is 1. So if we just substitute, we shall find out it is the limiting value is 0. Now it is the different type of questions. So I tell you that if the indeterminate forms are of the form 0 to the power 0 or infinity to the power 0 or 1 to the power infinity, then we just take the log on both sides. So accordingly here we take the log on both sides so that it is becoming in the form of this form. So if this form we find out, then to solve this one we just take like this one, limit here, the limit will not change. Here the limiting value is, we should write y tends to 0, it is, we rewrite in the form x tends to 0, it is log of y, then is equals to, this one is limit x tends to 0, and that form we should write it as log of x plus of sin x divided by 1 upon tan x, that means it is cot x, we should write it down, and it is in the form of infinity by infinity. So now we take the derivative for the denominator and numerator. We shall find it out as, herefore we find out as 1 upon x plus sin x, and its derivative means it is 1 plus cos x. Then it is, and for this one it is 1 upon minus of cosec square x. So if we simplify this one, then we shall find it out as limit x tends to 0. Then for simplification, from here we just write it is sin square x, then it is 1 plus cos x and divided by x plus sin x, and this negative sign we just write it down on the outside. And this is, if we substitute x tends to 0, we shall find out it is the form 0 by 0. Okay. So now if we again take the derivative and after that we substitute, then suppose we take the derivative, here minus sign is in the outside, and after taking the derivative here we shall find out as sin cube of x plus 2 into 1 plus cos x, then sin x and cos x. Okay, and then divide it by, here from it is 1 plus cos x, and if we substitute the x limit, then we find it out. Here it is 0 minus of 0 by 2, so that is nothing but 0. So this is our limiting value. Now the one more question, here it is in the form of 0 to the power infinity. Here the same way we take the log value in this way, and after that when we are going to take the limiting value, that means here it is the limit x tends to 0 of y, then it is okay. One more thing, just let me tell you that in the previous question this is the value of log y. If we want to value of y only, then it has to be to the power 0, so that is 1. So the limiting value for this given one, this one is, it is 1, not 0. Okay, 0 for the log of y. Now similarly, because I told you that we should take the log and after that we take the anti-log also. So now for this one, if we just substitute, then here it is the limit x tends to 0, and then it is, we just rewrite as we have taken the log on both sides, so here it is the log should be substituted, so it is the log of e to the power x plus x divided by 1 by 1 upon x, means it is finally getting as x, and now it is in the form of, here the limit is given infinity, so in form of infinity by infinity. So for this format, what we will do, we take the derivative for the denominator and numerator, and if we shall take the derivative, then it is e to the power x plus x, and it is e to the power x plus 1, and then divided by it is 1. So this is, we shall find it out. So that means here now this is the if we just rewrite it as this one, so e to the power x plus 1 divided by e to the power x plus x. So for this one it is again in the form of here it is infinity by infinity, because here the e to the power infinity means infinity and this one giving us the infinity. So again we take the derivative and we find out e to the power x divided by e to the power x plus 1. Now if we just substitute the value of the limit. That means e to the power x means it is e to the power infinity, so it is infinity, so again in the form of infinity by infinity. And if we simplify, then we shall find it out it as e to the power x by e to the power x. That means it is, finally we find out as 1. So this is the value for the log of y, and for the value it is y is equals to e to the power 1, means it is the e, because we have to take the antilog. So this is our result. Here is one more question, and here also the same way we proceed. Here again log we have to take, and after that we just reconstruct in the form of 0 by 0 or infinity by infinity and solve just like the previous two. And this one is the final one. One more question, just we rewrite it in the form of 0 by 0 or infinity by infinity, and we should solve it out. So hope you can understand what the indeterminate form is and what is the L'Hopital rule, and based on that how to identify a given function, a given limiting function, that it is indeterminate or not, and if it is an indeterminate form, then which form it is. After identifying the form, we should transform into the 0 by 0 form or infinity by infinity form, and after that we should solve it. Now here something for you, it is the do by yourself question, and I hope you can observe these questions. These all are the very well known limiting values to you. These all are the standard limit, these are the limit formulas. So how to get the value for those limiting formulas, that you should find it out, because all those functions are the indeterminate form, and I hope now you can able to do this. Just solve it out and write me in the comment box that how you like this lecture. And in the next lecture I will explain that how this L'Hopital rule will come, that means the explanation of the L'Hopital rule. So thank you all till that. Have a nice day.